All right, so now we move on to Unit 6, and this is the first lesson, which is 6.1 Rational Expressions. So what we're going to do is we're going to define very, very short here, what is rational expressions, and then what do we need to be looking for in order to solve these sorts of problems. Now, starting off with terminology here. So algebraic functions, we can take any two quotient of algebraic expressions, and these can be things like the examples that are over on the right here. So just any sort of combination of different sort of exponents or radicals or operations between the two. And if they're in a quotient like this, we say, hey, you know what? All of these are considered to be algebraic functions of some kind, or more importantly, algebraic fractions of some kind. Then, when we look at something that is a rational expression, this is a very, very important distinction. I recommend you highlight this in your notes. When we talk about a rational expression, which is going to be the rest of this unit, it's an algebraic fraction, but where the numerator and denominator are strictly polynomials, where they're p of x or q of x, and we don't really care what these are in terms of the overall polynomial. All we care about is that they're typically going to be defined in terms of x or some sort of variable that we now need to realize that that denominator also can equal 0, but both of them need to be polynomials. Now, when we look at these, a polynomial is an algebraic expression that is added or subtracted terms where they have whole number powers, variables, and there is no sort of radical that is attached to them. So let's see some examples below here. They give us examples like 1 over x squared, m over n plus 1. If we look at all these examples, we see that there's a positive 1, a positive 1. This is a 1 and a 1 for the exponents here. The power here is 2 and 2 and 1. So we're like, these are all good. And then they give us this example where they say x squared minus 4. Why does this considered to be a rational expression? To be a rational expression, it has to be some polynomial over another. Well, we can divide anything by 1. So if you really wanted to, what you could do here is you could just be like, hey, let's just take this, put it divided by 1, and I'm going to make sure that's a little bit bolder of a line, divide this by 1, and this also makes it some sort of rational expression. All right, now all rational expressions are algebraic fractions. So we can't consider that in the opposite way. If we're looking above, not all algebraic fractions are going to be rational expressions, but all rational expressions definitely can be algebraic fractions. Okay, now very, very important here. We want to consider non-permissible values. In this unit, this is by far one of the most critical skills that we have to have, and by the end, we have to be very good at, is we need to figure out what are the values of x such that we have an expression that is defined. And if we figure out the values where it makes it undefined, these can be considered the non-permissible values. So very, very important. We need to make sure that we figure out where is the undefined values, and then we'll make sure to account for those. In a rational expression, a value that results in a denominator of 0, that's exactly what a non-permissible value does, is that if we look at whatever value that's going to become, and you'll see in some of the examples below, whatever that value we say the NPV is, if we were to substitute it into our actual algebraic fraction or our rational expression, it would eliminate the denominator to 0, and we can't have denominators of 0. The other important thing we need to note, and we really, really want to highlight, is the values which are determined to be the NPVs must be established before we cancel any terms, because we can't cancel terms until we've established them, or else we're going to miss them and we'll totally just overlook them, and then we won't be accounting for things that should be included and restrictions that should be included on the variable. Now, let's look at the check your understanding very quickly. Circle the expressions that are rational. Well, let's circle the ones that are irrational and cross them out. If I look at a square root of x, a square root of x in the denominator, this is a big no-go. The reason is because a square root of x can also be written as x to the 1/2, and we see that as not an integer in terms of its exponent, or it's not a positive integer, a positive whole number. Okay, we go to the next one. We see that there is a -1 on that exponent here, and we're like, yikes, we don't want to see a -1 there. I'm going to use a different highlighter. Maybe I use something like a pink here. This -1, this is bad for us. We need to have a whole number that is positive, so this is also not rational. Now, if I go over to my third example, this one seems all good because we can definitely take the square root of numbers. We just can't take the square root of a variable, and all the other values in the exponents are positives, positive whole numbers to be more exact. So I'm going to highlight this one as this is a good solution for us. This is a rational expression. Now, the other one, right away, we see it in the denominator. It's the cube root. A cube root can also be written as the following: x cubed, or cube root of x, is equal to x to the 1/3. If that's equal to x to the 1/3, let's make sure we just circle this and we say this is not a solution we want to consider. Lastly, to the 1/2, well, they're both whole numbers, they're both positive. Not that being negative would be that big of a deal, but we see this as, yes, this is a rational expression where it's a polynomial over polynomial. In this case, a constant over constant or monomial over monomial. All right, now let's start doing our first formal examples here. So for the first example, for each rational expression, determine all the non-permissible values. To do this, we need to make sure the denominator is factored. If it is, then we're good to go from there. So in this case, we can't factor 2x minus 3 anymore. So to get our MPV, we're going to say the following. Our MPV is where 2x minus 3 cannot equal 0. If we isolate this for x, we're going to end up getting where if I add the 3 across, so I go plus 3 and plus 3, this is going to give me 2x cannot equal positive 3. I divide both sides by the 2, divide by 2, divide by 2. We end up getting, and I'm going to shuffle this all up here so that it's out of the way there. There we go. Our MPV, which we're going to short form as our non-permissible value is MPV, it's where x cannot equal 3/2. Perfect. And I'm going to try not to condense it into the next problem there. So 3/2. There's our non-permissible value. Okay, let's go on to our next one. Well, we're going to have to factor this one. So let's start off by rewriting this as 1 over. What does this factor to? Well, it has to multiply to make 6, add to make -5. That means that it's going to be x minus 2 and x minus 3. If we state the values here, our NPVs cannot equal the opposites. So it cannot equal 2, or else this would become 0, and it cannot equal 3. And you can even write it just like this. So if you say cannot equal 2 and comma 3, this is also okay here. All right, now we go to our next example. Remember, we only need to consider the denominator here. I mean, we could factor it all. So we could be like x minus 7, x minus 2, because it has to multiply to 14, add to make -9. In the denominator, we recognize this is a difference of squares from our first unit or chapter 0. And then from here, all we care about is the denominator. We're going to be like our MPV for this one is going to be where x cannot equal 5 or -5. And the way to truncate that is just to write plus or minus 5. All right, in our last example here, or part D, we're going to say this is equal to, in the numerator has to multiply to 1, add to make -2. That means it's x minus 1 and x minus 1 divided by the x minus 1 that's already there. Well, in this situation, we need to look at the denominator and say our non-permissible value, or NPV, x cannot equal +1. If it's +1, it will end up eliminating it to 0. So that's our whole goal, is we're only looking at the denominator because that establishes what value would make the denominator 0 or eliminate the overall function to be undefined. All right, let's go to example 2, where we're not only going to state the restriction, but we're going to see it in kind of a different format than we may have seen before. The other ones, we just factored them using some normal factor methods. For example 2, we need to recognize that, remember from Math 10C when we factored by grouping? This is no different. We're going to take this and be like, let's group the first term, group the second two, and I'll make sure I underline this a little more formally there. So group the first two, group the second two. Now, in the process of grouping these, what I'm going to realize is when I group these here, I can then rewrite this as this is equal to, when I group them, it's going to be 1 over. In the first grouping, I see that there's an a squared common, and I'll leave behind an a minus 1. If I factor out anything from the second group, it has to be just -1. That's all I can really do because there's nothing else to bring, which means I'm going to flip both of those signs. This is going to become 1 over a squared minus 1 because we take the outside terms and put them together. And maybe I'll just rewrite that so it's a little more clear. And then in my second bracket, a minus 1. I can take this one step further, so I'm going to do that over off on this side here. And this is going to become equal to 1 over. And then we're going to take the difference of squares. A squared minus 1 factors to a minus 1 times a plus 1 times a minus 1. We could take that even one step further and just combine our a minus 1s. I can make this a plus 1 for my first binomial, and then for the second one, a minus 1 squared, because there's two of them. Now, our MPVs are just simply going to be where we say, therefore, MPV, x cannot equal plus or minus 1. Because if it was either 1 or -1, it's going to eliminate the denominator, and therefore we can't have that. Okay, let's move on to our next one here. So here's where we really formalize it and put it all together. To simplify a rational expression, we must follow the following steps, and we're going to follow these same three every single time. We're going to factor the numerator and denominator if possible, state the non-permissible values, then cancel any terms afterwards. So we'll always follow that same process. Let's do that for the first one here. I realize that I can expand this numerator to become 4 squared is 16, a3 times 2 is a6, c1 times 2 is c2, over 6ab. Now what I can do is be like, well, in the denominator, I have a couple variables here. So I'm going to go NPV. We have a, which cannot equal 0. We also have b, which cannot equal 0, because if they were, it would wipe out the whole denominator to 0. Now I'm going to cancel this and go 16 divided by 6. They both divide by at least 2. I can rewrite this as 8. A6 over A1 is A5. C2 divided by nothing is just C2. In the denominator, we had 3 because we divided 6 by 2. And then the A was gone. We had 1B to include here. There's your final solution here. So not only do we have our MPVs, but we also have our terms. Okay, let's go over to B. Now, this is going to be a common trick we do with this one. I'm going to factor out a 2 here, leaving us with x minus 1. In the denominator, you're looking at this and being like, well, in the numerator, we have 1 minus x. In the denominator, we have 1 minus x. In the numerator, we have x minus 1. In the denominator, we have 1 minus x. To make them look the same, let's just factor out a negative, and then I can flip the signs of the denominator terms. Now what I'm going to do is state my MPVs. So I'm going to go MPV x cannot equal the opposite of the interior bracket, which is x cannot equal 1. From here, I can then do my cancellations and go, well, if there's an x minus 1 and an x minus 1, now I can state this is equal to, in my final answer, it's 2 over negative 1, which is just another way of saying negative 2 is the solution. Perfect. But remember, before we do cancellations, make sure that you are accounting for the MPV. Okay, let's go to our next one here. In this example, I'm going to try and factor out a term in the numerator. So I'm going to factor out 2, leaving me with 3 minus b all over. We recognize a difference of squares in the denominator, b plus 3, b minus 3. Now, we see in the numerator that these terms kind of look the same, but they're opposite. I'm just going to remove out a negative in the numerator. This is going to become negative 2, and now I can flip this to b minus 3 instead, divided by the b plus 3, b minus 3. Let's make sure we state our MPVs right away. As soon as we've factored it, let's state them. So it's going to be b cannot equal plus or minus 3. And as soon as we do this, now we can cancel terms. Our b minus 3s are a common binomial. I can wipe those out. This is going to leave me with the following. Negative 2 divided by b plus 3. And that's going to be my expression left behind. So I'll make sure I highlight that here. Perfect. Okay. Now let's go over to D. With D, this one requires that we do decomposition. So we're going to have to do a little bit of work off to the side with factoring these first, and then we'll go and put them into the equations here. So what I'm going to do is off to the side, because I recognize this requires decomp, I need to, in the numerator, multiply to make 72, add to make negative x. That means my values are going to be 6x squared minus 9x plus 8x minus 12. I'm going to factor by grouping. I'm going to remove out a 3x, leaving me behind with 2x minus 3. I see 8 and 12 both divide by 4, so I'm going to take out a 4 and leave behind 2x minus 3. Now I take one of those common binomials, and I pair together the outside binomials, and this becomes my numerator. Now I'm going to do the same thing with the denominator. So I'm going to take this and be like, what multiplies to make 12 adds to make negative 7? It's 2x squared minus 4x minus 3x plus 6. I factor by grouping. I take a common term out of the first, leaving me with x minus 2. I take out the negative 3, leaving me with x minus 2 here, because 3, if I remove 3 from this second grouping here, this puts the 3 out front. I then go, well, the x was left behind. If I divided 6 by negative 3, it gives me negative 2. Now I'm going to put together one of the outside binomials, and then, or one of the common binomials, and then pair together my outside terms. So these are the terms that I'm going to hold on to for my numerator and denominator. Now, let's substitute those in here. So this is going to be equal to, off on the side here, I'm going to go 2x minus 3, our bracket 3x plus 4. There we go, all divided by, I'm going to take the x minus 2 and the 2x minus 3. Okay, now I'm going to state my MPVs. As soon as I've factored it like I have, my x's cannot be equal to, and in this case scenario, my x's can't be, so let's just state MPV. X cannot be positive 2 or 3 over 2. If you isolate the x terms in the denominator terms, you're going to figure out that these would be your two values here. Now I can make my cancellations. As soon as you figure out what your MPVs are, if there's a common binomial, get rid of that piece. This is going to be equal to, and let's make sure I match the color here. This is going to be equal to 3x plus 4 divided by x minus 2. And once you get to this stage, you don't need the brackets. Unless there's multiple binomials, you can leave it as this. And this would be your final solution here. All right, now let's go down to part E. In part E, we're going to factor it just like we've done. We recognize a difference of squares, so x minus 9, x plus 9, because the a squared minus b squared results in a minus b, a plus b in brackets. In the denominator, I'm just going to flip this around. I'm going to make it negative x minus 9. Because if I want to make these two look the same as each other, we can just remove out a negative. And you could do the same thing in the numerator if you wanted to. Now that you have it factored, we're going to go MPV. X cannot equal the positive 9, because if it's positive 9, the denominator becomes 0, which we don't want. Now I'm going to do my cancellation. My cancellation cancels the x minus 9s away, and I'm going to be left with, this will be x plus 9 divided by negative 1, which we could just rewrite as negative x. Actually, we could write it in a couple different ways. Maybe we write it like this, negative x plus 9. So we're just going to keep the negative out as a coefficient, as a common factor, and then this will be our solution here. Because remember, a negative can just be transitive. It can be in the denominator or the numerator. We just moved it to the numerator. All right, I go over to this example, F. I'm going to write this as equal to, we realize that we can remove out a 3, leaving us with 4 minus x in the numerator. In the denominator, we need to multiply to make negative 20, add to make 1. This means our factors are x plus 5 and x minus 4. At this stage, we want to state our MPVs. So our non-permissible values are where x cannot equal negative 5, because if it's negative 5, the denominator is 0, or where x is 4, because that would make the denominator 0. We then need to do kind of a precursor step here. I'm going to take the negative out of the numerator such that I can make the x minus 4 term that I'm looking for. So I'm going to go negative 3, x minus 4. I've flipped that inside bracket in terms of positives to negatives. And now from here, what I'm going to do is I'm going to go x plus 5 in the denominator, x minus 4 in the denominator. We're going to end up canceling our x minus 4 here. So because it's a common binomial and we've stated our MPVs, x minus 4 is gone, x minus 4 is gone, and therefore we get this is equal to negative 3 divided by x plus 5. Perfect. And then just make sure your MPVs are very obvious. So if you're in the process of writing your MPVs, you realize that they're not very obvious and that they're not like pointed out, you can always highlight them or star them or box them just to make them look really obvious. Sometimes I even like to just draw a little box around them, similar to the way you would do your answer, just to make sure that that's obvious. So now we take a look at example 4, where it gets us to write a rational expression in x with a numerator of 1 and a denominator with integral coefficients so that the non-permissible values are the blank. So whatever they give us. Now, in this case, remember, a non-permissible value comes from the fact that just like in quadratic equations, we always took the opposite value of what we saw in the brackets. From quad equations, we actually work backwards in a very similar way. They said, if the x-intercepts are blank, then what is the overall expression? This is no different. We're just going to work backwards from considering that these are NPVs where we are given values for x, we work backwards into the brackets, and then solve. So this is going to look like the following. For the first one, we're going to write this is equal to 1 divided by, because the numerator is 1, if NPV is 3 or negative 3, that means that the bracket that we were considering was positive 3. Because if we add a negative 3 in here, it becomes 0. If we look at our second bracket, it's going to be x minus 4, because if we put in a positive 4, this becomes 0. Now what we could do is just like a last kind of expression to this is we could expand it and collect the like terms. If we were to do that, it would give us x squared. 3x minus 4x gives us negative x in the middle, and then negative 3 or 4 times negative 3, opposite way of that, 3 times negative 4 will give us negative 12. So if they wanted us to expand and simplify, this is what it would look like. But I would even be happy with the other ones there. Because they say integral coefficients, it makes me think that we're looking for this piece here. Okay. Now, if I go over to part B, very similarly, we look at plus, minus 2, and 0. That means that if I wrote my factored form, or if I write my form that gave me my MPVs, the first one is going to be where we have x, because if I have just x in the denominator, then it can't be 0, because if it's 0, then it wipes out. My next two terms are going to be a reflection of if x, let's say the MPV was 2, then there must be negative 2 in the brackets. If x was negative 2, then it must be that it is positive 2 in the brackets, and here it is. There we go. Now this has integral coefficients. Again, we could expand this out and make it 1 over, and then if I expand this in, it's going to become x cubed. And then, actually, let's just do this part by part so you can see it all. X times x is x squared. X times negative 2 is negative 2x. Now, this all gets multiplied to the second bracket of x plus 2. That means if I just shuffle this over just a little bit so we can create a little bit of space for ourselves, this is going to be equal to over here. We're going to have 1 over, let me make sure I get this here, 1 over, it's going to be x cubed minus, or sorry, plus 2x squared minus 2x squared. And then our very last term is going to be a negative 4x. If I simplify this to the most simplified terms, our middle terms go away and we get x cubed minus 4x. So that would be our simplified polynomial expression where there's a polynomial in the numerator, polynomial in the denominator, and we're satisfied with that. Okay, now what if we look at part C? Create a rational expression that's equivalent to x minus 3 over 2x plus 5 for which we have certain MPVs. Well, again, let's just make sure we do a little quick underline here and be like, if they give us where x cannot equal to, they're essentially saying these are our MPVs, or the non-permissible values. If those are the non-permissible values, it means that's what the factors that were canceled. So let's write a rational expression that's similar or that is equivalent. It's going to be equal to, like so. We're going to write our first one, which was x minus 3. Next to that, what we're going to have to write is the factors that would have came out of this. So it's going to be, x is going to be, if it was negative 1, which is the MPV, it means this was positive. If the other one was 2 over 3, that means that if we solve this, we're going to multiply the 3 to the x. We're going to then say the negative 2 would come across here, which means this has to be positive 2 like this, because we want to always put the opposite of it. And then this is going to be divided by, in the denominator, we have 2x plus 5, and we need to repeat the exact same binomials that would have came from the expressions here. So we need to figure out that in this situation, if these were to cancel like this, this would be considered to be our MPVs here. Okay, and again, why we put these two is because they're going to cancel out, which would give us this expression here, but we need to account for them as MPVs, meaning they were originally here, and then they're just going to be opposite signs. So in the case of it being positive, I should actually probably put a, oh no, this is all good. We're good. I was going to say, if we have it as a negative, we have the positive in here. If we have it as the positive over here, then this would end up working, that this has to be the negative. Oh, and this should be a negative here between these two. That's my bad. So I'm going to make sure that this is a negative here, because if our MPV is positive, we need to have the negative version of that so that it would cancel to 0. There you go. So there's your equivalent expression for this one, and I'll make sure to highlight in green here. Perfect. Okay. Now we go down to example 5, and they say, are 3 over 5x and 3 over 5x with x minus 3 in the numerator and denominator equivalent expressions? Shortly, no. The reason it's no is, let's just double check here. So we got no, there we go. Because the NPV of the first expression is only x cannot equal 0 while the second expression, I shouldn't capitalize that, the second expression has NPVs of x cannot equal 0, but x can also not equal 3. So simply put, like as we're in the 20 level, it's going to be less important to us that we consider things like point of discontinuity. But the reason is, like if you want to even get more familiar with this, is they both share where x cannot equal 0. We agree with that because of the 5x. But because they have this x minus 3, although these would cancel out after we state the NPVs, we need to consider that there is going to be a point of discontinuity at x equals 3. So I'm going to even write that in here. Point of discontinuity. Or at the 30 level, what you're going to call a POD at x equals 3. Perfect. Okay. Now, again, this is more of a 30 level problem than it is a 20 level problem. So we just want to kind of like give you that initial kind of like indication of where you might go with rational expressions in terms of what we need to consider, that these aren't just simply the same. You don't just cancel them out and say they're the same. If they don't share the same NPVs, they're not equivalent expressions or rational expressions. Okay, last problem for today. We go into example 6, which says that a rectangular box has a length x. So I'm going to put x down here on the box. It says that its width is 3 centimeters shorter than its length. So over here, I'm going to go that this is x minus 3. They then say the height is 5 centimeters shorter than the length. So I'm going to write this as x minus 5. Perfect. Now that we have all of these in here, we can write out an expression for part A, which says determine the expression for the ratio of surface area to volume. Well, surface area to volume for part number A here, we're going to go that this ratio is SA over volume. To figure out the surface area of the box, we need to take each length and width and height and multiply them by each other and multiply them by 2 because there's 6 faces total. So it's going to be 2 times, let's say we take the length and height first, it's going to be x times the x minus 5 plus 2 times, let's say now we measure the length and width together, it's going to be x times x minus 3. And then if we do the widths together, it's going to be plus 2, or the width and the height, I should say, x minus 5 and x minus 3. And this is all divided by, to do the volume, we just multiply all the length, width, and height together. So it's going to be x minus 3, x minus 5, all put together here. And just to help you avoid this here, this goes to here, this goes to here, and then this piece goes to right here. Okay, awesome. Now, in this expression, what are the restrictions here? The restrictions are simply going to be just whatever comes out of the denominator. So it's going to be B. We cannot have, or our NPVs, our non-permissible values, are where x cannot equal 0, because if it's equal to 0, the whole thing eliminates to 0. X cannot also equal 3, because if it's 3, it goes away. And lastly, x cannot equal 5, or else this would go away here. So we got to be very careful here. Now, when they say think about each dimension in terms of the restriction, will it ever make sense that a width is 0 or a length is 0 or a height is 0? No, so that totally makes sense for this. 3 and 5 are just getting specific in terms of if they're 3 or 5, that means that they're going to wipe out all the terms because it might be this common value that would eliminate terms from the numerator and denominator in a way, or eliminate terms from the denominator such that maybe they're the same value. So if it's 3 or 5, the width or length might be the exact same and might be unaccounted for. So there's a couple reasons why that might happen where our 3 and 5s would not be included as well, but the big one for sure is 0 here. Now, some of you might be like, can we do any sort of simplification with the overall expression in part A? I mean, we probably could. We could bring all the polynomials together. We could expand them and simplify in terms of like making them trinomials or whatever we want to do with these, or expressions of polynomials. But I think this is good enough for how it is. We just want to make sure that we can write out the general ratio as such and then just state the restrictions such that we're not getting conflicting values for x that would make this go to 0, which is exactly what we don't want to have for a ratio, because any sort of surface area to volume ratio You shouldn't get 0 in this or an undefined ratio because that wouldn't make any sense for a physical object. All right, this is where you're going to want to go on to get some assignment work done. Try these textbook problems out, see what you can do. Again, the one above here, example 5, is more of a 30 level problem, but still be very aware that expressions are only equivalent if they have the same MPVs. And then things like these application problems, just always be looking for that denominator such that you can state your MPVs. All right, good luck.